Topic 9 is titled Conic Sections. We've already worked with one of the types of conic sections, a quadratic function, the shape of which is a parabola. But there are other conic sections known as circles, ellipses, and hyperbolas. They have similar characteristics to quadratics and some differences. We'll start with lesson 9.2, circles. We'll graph, write equations, and apply some real-world application. The definition of a conic section is a figure formed by the intersection of a two-dimensional plane and a right circular cone. Take a look at how the parabola was formed. They took the intersecting plane through one side of the cone, and you can see that kind of parabola shape it forms over on that bottom right-hand side. If we look at a circle, we're going to go perpendicular to the graph, which means we'll take a look at a different way to create our equation. In general, the way you designate any second-degree equation follows this formula, a times x squared. But you also can have a y squared term, and that gets a different coefficient. Each term can have a linear counterpart, so cx plus dy. And now I'm running out of space, so I'm going to give myself a little bit more room on that right-hand side there. There we go. And then you need a constant, and we'll default that to e. If all your variables and coefficients are on one side, we'll set that equal to 0. Depending on the parts that are given, you'll have one of the four unique conic sections. Let's start with circle for new ones in topic 9. A circle is the set of all points equidistant from a fixed point. And notice, like we said before, it's perpendicular to the base or the axis, so it forms a perfectly circular shape. The standard form for the equation of a circle has two parts. It depends on if your center is right at the origin of the graph or if it's translated into one of the four quadrants. If your center is at 0, 0, the template for a circle follows this equation, x squared plus y squared is equal to r squared. The x squared and the y squared would designate the center right in the middle. R squared on the right is the length of the radius squared. But you can always translate your center just like we could translate the vertex for the quadratic function. So another alternative would be if your center is translated to a point h, comma, k. Now h is designating a shift to the left or right, and k would be vertical. And what makes circles unique in this equation is that you'd have x minus h squared, and you wouldn't have to worry about foiling it. H just means that's the translated part of the center on the x-axis. We also have y minus k squared, and now that's going to move up or down in the opposite direction as well. The one part that stays consistent is the right-hand side, r squared. So these will be the two formulas we focus on in this lesson. To graph, you always want to know those key pieces of information. You want to first plot your center, and then we'll figure out the radius. Once you know the radius, we'll plot additional points for the boundaries of the circle. So we'll just say plot additional points. So let's look at each of the two examples on the right-hand side. In that first example, it says graph each circle by finding the center and radius. The left side of the equation will always default the center. The right side will always tell you the length of the radius. It always works that way. In our first example, notice we have x squared plus y squared. If nothing's being translated from those two variables, the center defaults to 0, 0. So go ahead and plot the center on your graph. Now the right-hand side is always r squared by definition. So to get r by itself, we'll take the square root of each side. And we've done this before. R would equal plus or minus the square root of 15, which means we can go the square root of 15 units in any direction. Now the square root of 15 isn't super user-friendly, so in this case we can actually approximate this graph. The square root of 15 is approximately 3.9. It's pretty close to 4 because the square root of 16 would be 4. So to graph, what we'll do is from the center, I'll count 3.9 units to the right, so almost to 4. And I'll also count 3.9 units to the left because we can go positive or negative. Because y is being squared also, we can go up 3.9 on the y-axis and drop down to 3.9 on the y-axis. Using those 4 points, try to sketch your curve for the circle. Sometimes it takes a little bit of practice, and your circles don't have to be perfect, but we do want to designate those key features to sketch our graph. Over on the right, again the left-hand side, will determine where our center is located. And now we have a translation. What this means is that we'll take the opposite direction for each parenthesis. If it's x plus 3, that means it translated 3 units to the left. Our center goes to negative 3. And get this, if it's y minus 2 squared, then it actually would go up 2 units on the y-axis. Go ahead and plot negative 3, 2, and that's our translated center. I'm going to move that down just a little bit. There we go. Now the radius, remember, comes from taking the square root of the right-hand side. If r squared equals 9, at least it's a perfect square for this one, which is kind of nice. We'll get r equals plus or minus 3. So from the center, count 3 units to the right. That's on the boundary or the perimeter of our circle. 3 units to the left. We'll count up 3 and down 3. Okay, like last time, try to draw a smooth curve through those 4 boundary points. I find the more times I go around the circle, the more circular it looks. Just try not to make it a triangle, or not triangle, a rectangle or something, and get through those 4 points as best you can. If you know the center and the radius, you can write the equation in standard form just by following the formulas up above. When writing an equation, you want to plug in your center first. Either your center will be 0, 0, or it'll be the h and k, and we'll use opposite signs in our parentheses. Set it equal to the radius squared on the right-hand side. And that's really all we have to do if we know these pieces of information, which is kind of nice. Let's take a look at our first example. It says the center is 0, 6. That means we have a translated center. I'm going to write h and k up above. Now by definition, we would do x minus h squared when we translate our center, plus y minus k squared equals r squared. Now the h coordinate is 0, so when I plug that in, that's just x minus 0 squared. The k coordinate is 6, and that would give me y minus 6 squared. And then on the right, the radius is the square root of 5, but we're going to plug that in and then square it. So from here, all we have to do is simplify. X minus 0 is just x. That would default our formula just to x squared. Y minus 6 doesn't simplify, and again, we don't have to FOIL, which is really nice. We can leave it in this form. On the right, the square root and the squared cancel, and the radius squared equals 5. And that's it. That's the equation of this circle with a center at 0, 6 and a radius of the square root of 5. If you're given a picture, we just have to find the information we need from that picture. Counting to the left and up, it appears the center is at negative 5, 4. And then from the center, it looks like it goes 2 units to the right, 2 units to the left, up 2 and down 2. The radius is 2 units. Pause the video and see if you can write the equation for the standard form of this circle using that information. If you got x plus 5 squared plus y minus 4 squared equals 4, you've successfully written the equation for the circle graphed in example B. Let's try some application. A city wants to honor hometown veterans with a new memorial statue in a local park. A grid map of the park shows the statue inside a circular fence of radius 5. Let's go ahead and underline radius 5. That looks like it's going to be some good information. 2 spotlights are shown at points 2, 2 and 10, 8 on the map. They are the endpoints of the diameter of the circular fence. What equation represents the graph of the fence on the grid map? If we want an equation and it says that the fence is the shape of a circle, we're going to write the equation of a circle. So taking a look at the information, we already know the radius is 5, so we're partway there. We need the center. We don't know that yet. If the statue is going to be right in the middle and the spotlights are showing on it, remember it said they were on the endpoints of the diameter, which means that the statue should be right in the middle of those. So if we count up and over, I notice from 2, 2, if I count all the way over, and then up to the other spotlight, that would go from 2, 2 to 10, 2 over here on that right-hand side. Meaning the distance from left to right is 8 units, and the distance from bottom to top would be 6 units. Now if we want that statue right in the middle, that means I'm going to cut the 8 in half here, and the 6 in half on the right-hand side, which means I've gone 4 units to the right from that spotlight, and then it looks like I've gone up 3 units to get to the center. So if we were at 2, 2, and we go 4 to the right and up 3, our center would be at 6, 5. And then if we went over 4 and up 3 again, guess what? We'd end up at 10 and 8. So just by doing a little work with a triangle inside that circle, we were able to find those key parts that we needed. The center is at 6, 5. So just like the examples before, let's write the equation based on our model for a translated center of a circle. X minus h squared would be x minus 6 squared, plus y minus k, which is y minus 5. I almost wrote k, but that's all right, I didn't. And then on the right, we take the length of the radius and square it. Let's just simplify the 5 squared, x minus 6 squared, plus y minus 5 squared equals 25. That is the equation that represents the boundary of the fence for that memorial park. Now they say an information kiosk is planned. One possible location is represented at the point 9, 1 on the map. Should the kiosk be there, or should it be moved so that it doesn't interfere with the fence? Support your answer. So let's see. So at 9, 1, count over to 9 and up 1. Kind of looks like we're right here, doesn't it? I think that's where 9, 1 is. So if they want to put an information kiosk there, we got to make sure that it doesn't interfere with the boundary of the fence. To do that, we'll test 9, 1 in our equation. If our answer when we plug it in equals 25, then it's right on the circle. If our answer is bigger than 25, we'll be outside of the circle. And if it's less than 25, we would be somewhere inside the circle. And that seems to be the optimal place. So let's see what happens. If we plug in 9 as x and y as 1, we would get 9 minus 6 squared plus 1 minus 5 squared. Let's see how that relates to 25. 9 minus 6 is 3, and we'll square that. 1 minus 5 is negative 4, and we have to square that. 3 squared is 16. Be careful here. Negative 4 squared. Wow, never mind. You be careful. I need to be careful. Let's try that again. 3 squared is 9, and negative 4 squared is actually positive 16. And that equals 25. That means the kiosk is right on the fence. So they need to move it. All right, we will finish the rest of our notes in class.